The purpose of this video is to chat about 1.3 growing dots, the Desmos activity. If you have already done this Desmos lab, thank you for putting in that work. Thank you for watching this video so that you can take another look at representing geometric sequences with equations. For example, 3 parentheses 2t equals d, with tables, in this case dealing with the number of minutes and the number of dots. Continuing to talk about graphs, which you might have not graphed out when we were working with this, but we'll have that opportunity here. We'll take a look at the number of minutes and the number of dots based off of a growing succession and story context. We don't have a big story as to why these dots keep increasing in numbers, but that's okay. Hope that you're having a great day. Let's get started. So these are all helpful things, different ways that we can express a geometric sequence using an equation, a table, a graph, or describing it verbally with what's going on. Sounds good, right? You had this first piece here where if we were starting, disregard how this says 1 dot, this is actually starting with 3 dots, where all you had to do in this case was just fill in the table, which I don't think is too taxing of you. I think you have the time. At the beginning, which what they write here is 0 minutes, hopefully we can agree that there was only 3 dots, whereas at 1 minute there was 6, at 2 there was 12, at 3 minutes there was 24, at 4 minutes there was 48. What pattern did you see as this went on? Hopefully you're saying something to the effect of how we are doubling the previous number. So on the sidelines, you would want to write something to that effect. I think it's important, is that your current term is equal to the previous times 2. Makes sense to me. So if this were to continue for 5 minutes, hopefully we would just be able to take 48 times 2 and get 96 dots. And then this approaches towards t, where this was a tricky part, but I mean, think about what we said in words. We said that we kept taking the previous times 2. So here we just started with 3 versions of 1 dot. Here we took still 3 versions, but then we have 3 versions of 2 dots. Here we had 3 versions of 4 dots, or you could rewrite this as 3 times 2 times 2, also known as what? How can you rewrite this? Hopefully you're saying 3 parentheses and then 2 squared. You guessed it, down here this would be 3 parentheses 2 to the 3rd. This would be 3 parentheses 2 to the 4th. 3 parentheses 2 to the 5th. So if this was approaching t minutes, where t is any number, well, how is that going to switch this up now? What's the new exponent? Hopefully you're saying t, and this is again dictating the number of dots, where d is the number of dots. So this is what you should have had for this first one. Pause the video, copy this if you don't have it, but this is what you need. All right, and if we were graphing out these findings, this doesn't take too long. Recall that at the very beginning, we only had 3 dots. And then at 1 minute, we had 6 dots. At 2 minutes, we had 12 dots. Then 24. Then 48. And you soon start to see that this gets pretty wild. which is normal. That can happen. So the graph would look something like that. Sounds good. Let's see what else is coming down the pike on here. So if we hit next, we're describing in words how many dots there are. Well, we said that this was already the previous times 2. That equals the current. And we're also starting with 3 dots. So you would write that. For the recursive, we start to fall back on what this means. How many dots at 1 minute earlier is going to be a pivotal thing here. So we start at the very beginning. So whenever we think of recursive, think of starting at the beginning with the very first pattern. I might go back and forth between calling it the beginning term or the start term. Those terms are very helpful. And that really is pivotal when we're talking about this recursive equation. Okay, so this is saying if we have f of 0, this means at 0 minutes, how many dots are there? Recall that there were 3. And then this snowballs into f of t, where we don't just want to say that the current equals the previous times 2. Reason being is that we're now working in function notation. So f of t is going to stand for our current minute, whatever that minute is. And the previous, we can refer to that as f of t minus 1. And then what else do we need for this part of the equation? Hopefully you're saying times 2. And boom, that's our recursive equation that would work here. Pause the video or copy this if you don't have it. And as we move towards the explicit, this tells us how many dots there are. If we know how many minutes have passed, well, this can always vary. So we already found this on the previous page. This is 3 parentheses t to the, 3 parentheses 2 to the t power. Boom. And as we take this further, we were talking about how the table is different. We see that we're no longer adding 4 or subtracting 4. Be open to using multiplication or division. For the graph, this is no longer a straight line. This has a curve to it, as we saw. For the formula, this now has exponents. Whereas before, we just had linear straight lines. So, hope that helps. We see a geometric sequence, a sequence with a common ratio between consecutive terms. So this is a dead giveaway that we're probably going to work with an exponent in our equation, because if we had our table from before with minutes and the number of dots, we had minutes 0, 1, 2, 3, 6, 12. If this common ratio holds up for all of our points, and they're all set equal, then chances are we're working with a geometric sequence. So if I took this number of 12 and claimed that this was my next, and then I continue to take my number of 6 and claim that this is my previous, what would that common ratio be? Hopefully you're saying 12 over 6, which can be simplified to just positive 2. Another option is that you could have taken 6 over this 3 Is that really going to be any different? No, it's not any different. Positive 2 still. And so since these both hold up, our common ratio in this case is positive 2, which is interesting because recall, we were taking the previous times 2, and that was equal to our current number of dots. Pause the video, take a note on this. This video explains why we end up with 1 if our exponent's equal to 0. I'll put that in the description. There was this challenge activity, which I'll actually give a shot. So at the very beginning in this situation, we would say that f of 1 has 3 dots, and that as this continues, this is still doubling. So you would say f of t is equal to f of t minus 1 times 2. So that would be your recursive. Because we're recalling our beginning, our starting term was f of 1. And for the explicit, do we know how many dots there are at 0 minutes? Well, we know that this is still doubling the previous minute, so if we took half, this would have to leave us with 1.5 dots. If you're not convinced, you can try it out, but at 0 minutes, we would have just kind of tough to write the half dot, but this is a half. We definitely start with 1/2, so starting with 1/2. And sometimes the table helps us here. So we have 0, we have 1.5, then we have 3, then we have 6, then we have 12. So as this starts to continue, we see that we have 2 versions of 1.5. Here we have 4 versions of 1.5. Here we would have 8 versions of 1.5. So this 2 just keeps kind of changing, but 1.5 is pretty steady. Okay, so we could say that no matter what, we have that 1.5, and then we have parentheses and then 2 to the t power. And so if you're not convinced, you could try this out. But 1.5 is definitely steady. That's always at the very beginning, meaning at 0 minutes. And then the number of dots, of course, changes based off of that. What's cool is that if you plug back in any of these minutes, you should get back to the number of dots. I hope that this video was helpful. If you have any questions, reach out. Thanks for watching.